Hi students, this is Dr. Joe Angley. We are now getting ready to start our study of energy. Because there's a lot of material in this chapter, I've broken it up into 3 lecture videos. This first lecture covers fossil fuels. The second lecture will cover nuclear power and hydropower. The third lecture video will cover what are termed renewable energy sources. This slide presents the learning objectives for this lecture. You should review these objectives on your own. Also note that as you proceed through the lecture, you will be asked to answer various questions. It may take additional research and independent thinking to answer these questions, so please be on the lookout for them. In addition, there are questions to be answered at the end of the lecture. Please bring your answers to all the questions to class and be prepared to discuss them and present some of your results. The former Saudi oil minister, Sheikh Yamani, noted that the Stone Age did not end because we ran out of stones. In the same way, the fossil fuel age will not end because we run out of fossil fuels. In fact, as we will learn in this lecture, we have thousands of years of fossil fuels left to exploit. With so many years of fossil fuels available, why do you think we shouldn't use them? Stop the video now and write down some ideas on why this might happen. Oil, coal, and natural gas are the fossil fuels that we typically think of when we consider energy sources. But fossil fuels also include less conventional sources such as tar sands and oil shales. Fossil fuels are formed from fossilized plant material preserved by burial in sediments and compacted and condensed by geological forces into carbon-rich fuel. Most fossil fuels were laid down during the Carboniferous period some 286 to 360 million years ago. Because these fossil fuels took so long to form, we consider them to be non-renewable resources. The fossil fuels, coal, oil, and natural gas, that have powered the industrial age have brought us many benefits, but have also caused huge social, political, and environmental problems. As we learned in our discussions of climate change, perhaps the most threatening of these problems is that the burning of fossil fuels emits carbon dioxide, CO2, which is changing our global climate. We now get nearly 90% of all commercial energy from fossil fuels. How we'll end our dependence on, some would say addiction to, fossil fuels is one of the most important problems that face us today. In this chapter, we'll look at the costs and consequences of various energy sources, as well as our options for the future. In this lecture, we'll start with the fossil fuels. In later lectures, we will cover nuclear and hydropower, and then turn to renewable sources that could supply all the energy we will need in the not too distant future. To understand the magnitude of energy use, it is helpful to know the units used to measure. Work is the application of force over distance, and we measure work in joules. Energy is the capacity to do work. Power is the rate of energy flow or the rate of work done. For example, 1 watt equals 1 joule per second. If you use a 100-watt light bulb for 10 hours, you have used 1,000 watts, or 1 kilowatt hour. Most American households use about 11,000 kilowatts per year. This table shows the energy consumption of some common household items. Based on this table, what appliance uses the greatest amount of energy in your home? Stop the presentation and go find out how much power your cell phone uses in 1 year. How much money do you think it costs to charge your cell phone for a whole year? Like most industrialized nations, the United States gets a vast majority of its energy from fossil fuels. According to the U.S. Energy Information Agency, oil currently provides 37% of this supply, followed by natural gas, 25%, and coal, 21%. Renewables, hydro, wind, solar, biomass, provide 11%, and nuclear power supplies 9%. In the 20th century, the rich countries of the world although they made up less than 5% of the total population, consumed more than half the commercial energy. That situation is now changing, however. Rising incomes in China are leading to more energy consumption. China now consumes as much primary energy as all of Europe, and 85% as much as the United States. And because so much of China's energy comes from coal, it has now passed the United States in total carbon dioxide production. The so-called renewable energy resources that make up approximately 11% of our generating capacity, this is expected to change over the next century. Why do you think this may happen? This slide shows the distribution of the world's mineral fuels. Reviewing this map, what parts of the world have the greatest abundance of coal? What parts seem to have the greatest abundance of oil? What continent has the fewest mineral fuel resources? The largest share of the energy used in the United States is consumed by industry. Mining, milling, smelting, and forging of primary metals consume about 1/4 of that industrial energy share. The chemical industry is the second largest industrial user of fossil fuels, but only half of that use is for energy generation. The remainder is raw material for plastics, fertilizers, solvents, lubricants, and hundreds of thousands of organic chemicals in commercial use. Residential and commercial customers use roughly 41% of the primary energy consumed in the United States, mostly for space heating, air conditioning, lighting, and water heating. Transportation requires about 28% of all energy used in the United States each year. Almost all of that comes from petroleum. About 3/4 of all transport energy is used by motor vehicles. World coal deposits are enormous, 10 times greater than conventional oil and gas resources combined. Coal seams can be 100 meters thick and can extend across tens of thousands of square kilometers that were vast swampy forests in prehistoric times. The total resource is estimated to be 10 trillion metric tons. If all this coal could be extracted, and we could find environmentally benign ways to use it, this would amount to several thousand years' supply. But do we really want to use all that coal? Almost all the world's coal is in North America, Europe, and Asia, and just 3 countries, the United States, Russia, and China, account for 2/3 of all proven reserves. Coal is mined in 2 ways, underground mines and surface mines. Surface mining is used for deposits that lie within 100 to 200 feet of the Earth's surface. Coal mining is a dirty, dangerous activity. Underground mines are notorious for cave-ins, explosions, and lung diseases such as black lung suffered by miners. Underground mining involves more human labor than surface mining. Historically, coal was dug by hand by coal miners. Today, underground mines are highly mechanized with machines doing the digging, loading, and hauling in nearly all the mines. Even so, underground mines need more laborers than surface mines. Between 1870 and 1950, more than 30,000 American coal miners died of accidents and injuries in Pennsylvania alone. Thousands have died of respiratory diseases. Black lung disease and inflammation and fibrosis caused by accumulation of coal dust in the lungs or airways is a common disease found in miners worldwide. China currently has the most dangerous mines, with 91,172 killed in mining accidents in 2008. Surface mines, called strip mines, where large machines scrape off overlying sediment to expose coal seams, are cheaper and generally safer for workers than tunneling, but leave huge holes where coal has been removed and vast piles of discarded rock and soil. Strip mining is cheaper and safer than underground mining. However, it makes land unfit for other uses. A common environmental issue associated with coal mining is acid mine drainage. Acid drainage damages streams. Mountaintop removal, practiced in Appalachia, causes streams, farms, and even whole towns to be buried under hundreds of meters of toxic rubble. An especially damaging technique employed in Appalachia is called mountaintop removal. Typically, the whole top of a mountain ridge is scraped off to access buried coal. Mountaintop removal, practiced in Appalachia, causes streams, farms, and even whole towns to be buried under hundreds of meters of toxic rubble. In 2010, the EPA announced it would ban valley fill, in which waste rock is pushed into nearby valleys, but existing operations are grandfathered in. Mine reclamation is now mandated in the United States, but efforts often are only partially successful. Coal burning releases huge amounts of air pollution. Every year, the roughly 1 billion tons of coal burned in the United States, 83% for electric power generation, releases close to 1 trillion metric tons of carbon dioxide. This is about half of the industrial carbon dioxide released by the United States each year. Coal also contains impurities such as mercury, arsenic, chromium, lead, and uranium, which are released into the air during combustion. The coal burned every year in the United States releases 18 million metric tons of sulfur dioxide, SO2, 5 million metric tons of nitrogen oxides, NOx, 4 million metric tons of airborne particulates, 600,000 metric tons of hydrocarbons and carbon monoxide, and 40 tons of mercury. This is about 3/4 of the sulfur dioxide and 1/3 of the nitrogen oxide released by the United States each year. Sulfur and nitrogen oxides combine with water in the air to form sulfuric and nitric acids, making coal burning the largest single source of acid rain in many areas. Most people aren't aware of it, but coal burning plants emit radioactivity from uranium and thorium. You'd get more radioactivity living 70 years next to a coal plant than next to a nuclear plant, assuming no accidents at the nuclear plant. It's possible to make either gas or liquid fuels out of coal, but these processes are even dirtier and more expensive than burning the coal directly. Both coal to liquid and coal to gas are environmentally disastrous. In 2010, the United States Energy Information Agency predicted that coal would drop to 44% of America's electrical generation by 2035. Actually, we reached that level in 2011. Currently, the government is projecting that coal will provide only 39% of our electricity by 2035, but that estimate appears to be still far too high. In reality, coal is fading quickly from our energy picture. Only half a dozen new coal-fired power plants are now under construction or in the planning stage. When the last of those plants is finished, about 5 years from now, no other new projects are proposed for the foreseeable future. Federal regulations are part of this decline. The mercury and air toxic standards announced by the Environmental Protection Agency in 2012 will slash the allowable mercury emissions from coal-fired power plants. This was required by the 1970 Clean Air Act, but it was delayed for decades by owners of old power plants who argued that their facilities are about to be closed anyway, and so they shouldn't have to install expensive pollution control equipment. 40 years later, many of those plants are still in operation and still emitting dangerous pollutants. The EPA estimates that new rules will cost utilities about $9 billion, but will save $90 billion in healthcare costs by 2016 by reducing our exposure to mercury, arsenic, chromium, and fine particulates that cause mental retardation, cardiovascular diseases, asthma, and other disorders. In 2012, the EPA also proposed limiting carbon emissions from power plants. If this rule goes into effect, new facilities will be allowed to emit no more than 1,000 pounds, 454 kilograms, of carbon dioxide per megawatt hour of electricity produced. Natural gas plants can easily meet that standard, but it's about half the amount released by the average coal-fired power plant. The only way to meet this limit with coal is to install expensive carbon capture and storage equipment. As of spring 2015, the United States Supreme Court is still hearing cases that may invalidate or modify the EPA carbon emissions regulations.